So in terms of working projectile motion problems, again, the big idea here is that these are kinematic problems. So we're going to do the same thing we did when we're working any other kinematic problem. It's just this is the one situation that we're going to focus on where we can have two-dimensional kinematic motion. Here again, let's think about throwing a projectile horizontally off the top of some height. So whether this is a building, whether it's a cliff, I'm going to throw my projectile horizontally. It's going to hit the ground, and just before it hits the ground, it's going to be traveling with some velocity that points down below the horizontal. I know that during its motion, it's going to have an acceleration vector that points straight down. And then I can pick a coordinate system, and once I pick a coordinate system, and in this case I'll just happen to put the origin at the base of the building where I let the object go, I can draw in initial and final position vectors showing where the ball was when I let it go initially and it started being a projectile, and where it was right before it hit the ground and stopped being a projectile. The 5 vectors that I care about in a kinematics problem: acceleration, initial velocity, final velocity, initial position, final position. There they all are. And then I know I'm also going to care about time. Once I've picked my coordinate system, and again in this case I've picked positive x pointing to the right, positive y pointing up, I need to go through and break up all 5 of those vectors. The acceleration points straight down, so in this case it's going to have an x component of 0 and a y component that's negative. The velocity vectors, the initial velocity vector points entirely in x. The final velocity vector is going to have the same positive x component but a y component that points downward. It's going to be negative given my choice of coordinate system. And then again I can do the same thing for the position vectors. The initial position vector points straight up along the y-axis. The final position vector points to the right along the x. So when I set up my table for what I know, the acceleration, again, it has an x component of 0 and a y component that's plus or minus g, and that's always known. All right? By definition, having a projectile means that's what the acceleration is. When I think about the other components, again, I break them up just like we were talking about in the previous slide. What I do know is that the initial and final x components for that velocity vector have to be the same. Time is a scalar, not a vector. So it's not the x and y components of time, it's simply that my projectile is traveling the same amount of time horizontally as it is vertically. So it's still a scalar, time is still a scalar here, but it's the same value for time that's going to describe both my horizontal and vertical motion. Now in terms of some special cases, right? If my object is thrown horizontally or dropped, the initial velocity is 0. If it's at its highest point, whatever point in time that is, the y component of the velocity is 0. If it's thrown straight up, that's a one-dimensional problem, or if it's dropped straight down, that's a one-dimensional problem, and so all the x components will be 0. So when I'm thinking about the equations that are going to be most helpful, is the acceleration of my projectile 0? Well, the answer is yes in the x direction, which means that I have a single equation to describe horizontal motion, and it is often useful to, once you set up that table, to go ahead and set up your horizontal motion equation to see if anything pops out. Often it won't, but sometimes you'll basically be able to solve for some parameter right there, right away, and that'll make working the rest of the problem much easier. Now obviously the acceleration is not 0 in the y, but we do know that it's constant. So again, now that means that I can use one of my 3 constant acceleration equations to describe the vertical motion of my object. So in this case, if I want to know time or if I'm told time or want to know time, then again I'm probably going to start by using my equation that describes the vertical motion without using time, my v-squared equation. Or if I do know time or need to know time, then again I have my 2 position and velocity functions for the vertical motion as functions of time. So I have 3 equations that describe my vertical motion and 1 equation that describes the horizontal.